Okay, so we're going to talk about creep, which is the last section of Chapter 8. Creep deformation is a relatively slow process. I guess it doesn't have to be, but typically it's a slow process. It's a deformation that occurs at constant stress, and most of the time we think of this as being a process that occurs at a relatively high temperature. Well, elevated temperatures, let's call it. For example, you may think of creep occurring in a turbine blade. You may think of creep occurring in a structural component for a furnace or some type of thermal part. So when we have the stress and it's turned on, we have a creep strain, E, versus time, then looks something like this. So here in the front, at time t equals 0, we have the instantaneous deformation. So this is the strain that happens when load is first applied. You can think of this as the initial elastic strain. This is then in this region here, we have a relatively long period of constant strain rate, and this, we have some delta T versus delta E, and this is what we call the region of secondary creep. This part is then primary, and this is ternary. And up here we have rupture. So in this primary region, you have the mechanisms of creep initiating. You have, for example, one of the primary mechanisms of creep is through the diffusion of vacancies in a crystal, and you may have these just getting started. You might have, say, a surface that acts as a source of vacancies, and they start turning on. In this middle region, we have most of the lifetime of the part, in which we have this kind of slow diffusion of vacancies. You might also have, for example, some type of grain boundary sliding, and in which these grains in this region start getting themselves aligned, and then in this region, the grains are able to slide past each other very slowly, and again, the grain boundary sliding is assisted by defects. And then in the ternary creep, that's the point where there's voids and thinning in regions which lead to rupture within a period. You can think of it as approaching a failure. So as I said, this is typically a thermally activated process. So if we have our strain versus time, if we have, say, one part and it does something like this. We might have another that does something like that. And this corresponds to increasing temperature. As you increase the temperature, then the strain rate increases, the strain rate being the slope of the strain versus time curve. And that's because typically the processes involved are thermally activated. So we have that Arrhenius relationship that tells us about the activation for vacancies to hop or for there to be a small shift in a grain's positions. Now this is also a part that's under load. So instead of increasing temperature, you could have very similar changes in terms of the increase in the strain rate by increasing the applied load. And that's important because it means that basically you have two variables here. You have the temperature and you have the stress that are part of the system, and though those two are not independent of each other. So talking about this, we can also think about the lifetime, right? The point of rupture. Call that T rupture, say 1 and 2. So the average time to rupture, and again, this is a system that you'd want to run multiple tests on to get an average rupture time, but certainly at lower temperatures you would have a rupture time which is longer than at higher temperatures, and at lower applied stress you would also have a longer lifetime prior to failure. So if you think about that graphically, you can think of it as, say, the applied stress versus lifetime. Right, and you can think of that as being some relation. And as we increase the temperature, that's going to decrease the lifetime at a given stress. Increasing the temperature will decrease the lifetime, and the converse of that is that if you were to operate at a lower temperature, you would increase the lifetime. When we talk about this in a quantitative fashion, we recognize that this shape, it looks a lot like the fatigue rates, and turns out it also obeys a power law. And that power law behavior is the strain rate. So that is, sorry, we're using E's in this class. I mentioned earlier, when I've taught 413, we've always used epsilon, so epsilon, but yeah, epsilon to represent strain. So E dot, which is dE by dt, is equal to K1 sigma to the n. So this would be some constant, and that is our empirically determined that is our stress. Okay. Now, in this case, this constant is actually going to also carry with it the material information, right? Because we talked about these power law relations and the Arrhenius relations, and oftentimes you wind up with the materials information being carried in these coefficients. And in the case of this particular power law relationship, that's going to carry information about the thermally activated processes. And we can write another power law as K2, so that's just a second constant, exp negative Q, I'm going to call C for creep, RT sigma to the n. So that means this is the first coefficient, and this gives you the temperature effects. So this is a way to talk about the change in the strain rate with changing temperature and changing the applied load. Talking about mechanisms, I said it's largely a diffusion activated process, right, in which we have some part and it's under, let's consider it under tensile loading, and what's essentially happening here is atoms have to be diffusing away from this middle region and toward the tip or toward the edges, and that allows for an elongation and that's something like that. You can also think of that, though, as vacancies moving in the opposite direction, because we know from our discussion of Chapter 5 that vacancies are the dominant mode of deformation for common metals. Now, this picture is a little bit simplified because we know that our metals are actually polycrystalline grains, right? So this diffusion process has to be happening within the microstructure, and that's important because when you think about designing materials, you're actually thinking about designing a microstructure. So one way that you can think about the diffusion process is that you can think of it as vacancies that come through and they diffuse through the grain. And the process and the mathematics of this diffusion in grain, the mathematics of that was worked out, and we call this a Nabarro-Herring creep. And as you get more into the engineering literature, you're going to see some names over and over and over again. Nabarro and Herring were both, you can think of them as metallurgical engineers, metallurgical scientists. You might think of them as material physicists even, but they were very active in the field of material deformation. But I said that's one mechanism. But another mechanism is a mechanism in which you have vacancies, and they may move, but they will move along grain boundaries. And the same way, you can think of mass moving along grain boundaries. And you can imagine these grain boundaries, they're just a bunch of broken bonds that are kind of dangling there. That leaves a relatively wide gap and plenty of room for atoms to diffuse and vacancies to move as well. So that's actually a much easier pathway. And we call this cobalt creep. Cobalt creep is a grain boundary diffusion. Now, naturally, you know this is going to be typically is a lower temperature process. Because the energy barrier is lower, so our Arrhenius expression that we had for the activation is going to be smaller, and it'll be faster. This is typically a higher temperature process. But the interesting thing is, if you imagine, for example, these atoms, they're diffusing, well, and that's a low temperature. If you heat it up, they don't stop diffusing through the grain boundaries. Just, they start also diffusing through the body of the grain. So both these processes are active. So what you'll actually see is looking at the behavior as a function of temperature, you'll see what looks like very different mechanisms or very different behavior, and that has to do with the fact that you are seeing different behavior, because at low temperatures you're getting just through the grains. At high temperatures, you start higher, or middle range temperatures, you start getting try that again. At low temperatures, you only get grain boundaries. At higher temperatures, at medium range temperatures, you get both. You start getting a little bit of the through the grains, and then at high temperatures, these are both going to be active. So there is a transition between the regimes and a difference in the behavior. And a final comment about engineering and predicting the the rupture lifetime. We do this using what's called the Larson-Miller parameter. Your textbook uses an M for this. I've seen it used as a P for parameter. I've seen an L as well. So be aware that there's not necessarily a universal agreement on what constant to use, but typically it's considered the Larson-Miller method, or Larson-Miller approach to predicting creep lifetime. So the basic idea is that if you're given a set of say, stresses versus T rupture for, say, a couple different temperatures. Right, because the hot one's going to be shifted to the left here. And for example, you have a company, and the company invested, to get a couple data points. And you get these curves. Well, you can use these with the Miller-Larson equation is equal to C plus natural log rupture time. So that's the Larson parameter, that's the temperature, that is a constant, we'll come back to that, and that's the time to rupture. So this can all come from a few curves. Now, if you have this, and I should comment that C, that is a constant, is material dependent. For now, what you should know is that C is equal to 20 for low alloy steels. And if you go to high alloy steels, that's going to be C equals 30. You see, so if you have these, then in application you'll make a curve, or take this and you'll have a curve from it that will have stress versus M, because you have the stress here, and that's going to give you some curve. If you know the applied stress, you can go read your Miller-Larson parameter and then use that to get the rupture time. So take this plus this, find versus the temperature. So for a given temperature, how long will it last? And that's all we're going to say about creep. So this is going to be the end of chapter 8 from the text.